For section 9.4, we've already covered the divergence and integral tests. Now we're going to examine a specific pattern of series called a P series. Here's the definition of a P series. A series of the form sum from k equals 1 to infinity of 1 over k to the p, which expands as 1 plus 1 over 2 to the p plus 1 over 3 to the p, and continuing, where p is a constant, is called a P series. Now, just a heads up here, notice that P is a power, but we are not calling this a power series. This is intentionally named a P series. In Chapter 10, we're going to look at something called a power series, which is distinct from this P series that we're considering. So, P is a power, but we call this in particular a P series. If you recognize that you're dealing with a P series, then determining if it converges or diverges is a piece of cake. Here's the theorem. The P series, sum from k equals 1 to infinity of 1 over k to the p, converges when the power is greater than 1 and diverges when p is less than or equal to 1. Now, you can certainly memorize this theorem, but also try to connect your intuition so you can really understand how we're getting these conclusions. We're not necessarily going to prove it, but notice here, if p is greater than 1, the power is higher. If the power is higher, it's causing the denominator to grow faster. If the denominator is growing faster, the value of the fraction is decreasing faster. So as the terms of your series decrease, it turns out for a P series that the series actually converges. If p is less than or equal to 1, then this denominator will not grow as fast as it would with a power bigger than 1. If the denominator is a little bit bigger, the denominator is a little bit smaller, then the fraction is a bit bigger, the terms of your series are a bit bigger, and again, this ultimately causes the series to diverge. So I hope that helps you to remember the results, but also it helps to compare this to the geometric series. Some of the conditions that we're looking at here are reminiscent of the geometric series, but I want to point out they're the exact opposite. Recall that the geometric series has the form sum from k equals 0 to infinity of a r to the k. A is a constant. The common ratio r is what we examine to determine convergence or divergence. Recall that the geometric series converges when the absolute value of that ratio r is less than 1 and diverges otherwise. The P series looks a lot different, but notice how these two seem to be opposite, right? We're used to looking for the ratio of the geometric series to be less than 1 to conclude convergence, but here I'm looking for the power p to be greater than 1 to establish convergence. Same thing here. You can see the opposite going on. If the absolute value of r is greater than or equal to 1, the geometric series diverges, but the smaller p-value, p less than 1, is going to cause a P series to diverge. Now, the P series and the geometric series are distinct patterns, but because the results seem to resemble each other, I wanted to point out that difference to help you to keep all of these details straight. So let's examine a couple of P series. Example 4, determine if the following P series converge or diverge. So to determine if they converge or diverge, I want to express it in a way that resembles the basic format of a P series. So I'm going to rewrite this as the sum from k equals 1 to infinity. Now, by the way, the constant here can remain inside that summation symbol, or you can factor it out just like you would in front of a differential operator or the integral sign. Then I'm going to write this as 1 over k to the positive 3/2. That matches the pattern of our P series. So we can observe that in this case, p is 3/2, and that is greater than 1. Since p is greater than 1, this P series converges by the theorem on the P series. Pretty simple, right? I think you're going to like P series. Let's look at the next one. Sum from n equals 3 to infinity of 1 over the square root of n minus 2. Now, I do observe that that radical represents a 1/2 power in the denominator, but it's not just n under that radical, it's n minus 2. It would be convenient if it were just an n. We would like for it to look like this, because that's going to be a P series, right? 1 over n to the 1/2 power. So if I add 2 to the nth term formula, then I could offset that by subtracting 2 from my index. If I subtract 2 from 3, I get 1. And by the way, infinity minus 2 is infinity. So we could write this as the sum from n equals 1 to infinity of 1 over n to the 1/2 power. So this is clearly a P series. It matches the pattern. P, our power here, is 1/2. It is less than 1 because the power is less than 1 according to the theorem on P series. This series diverges. It's pretty simple and straightforward. Let's look at example C. This should catch your attention as a P series because the power, even though it's expressed as a radical, is remaining consistent, at least with that cube root across the denominator. So if we write this in symbolic form, we could say this is the sum from k equals 1 to infinity. So notice this is my first term, this is my second term, third term, fourth term. Observe that the radicand is the square of k. So we could write this as 1 over the cube root of k squared, or the sum from k equals 1 to infinity of 1 over k to the 2/3. So we're dealing with a P series. Notice P is equal to 2/3. This is less than 1. If the power is less than 1, then the series diverges. So this P series also diverges. For the last example, we have the sum from k equals 1 to infinity of 1 over k. Do you recognize this structure? He's pretty important. This is our harmonic series. Now, we already know that the harmonic series diverges. We proved that with the integral test. But we could also see this as a P series. Now, if we come back up here and look at the details of the P series, notice, oh, glad we came back up here to look. This should say less than or equal to 1. If the power is equal to 1, then the conclusion is that the series diverges. So looking at our P series here in the form of the harmonic series, we could say since P is equal to 1, the series diverges. So whether we prove that the harmonic series diverges by integral test or by P test, we are certainly consistent in that conclusion. So P series are easy to recognize, easy to make the conclusion for. Just make sure that you distinguish them from geometric series.